Hello, this is section 4.3 exponential functions and applications. Objectives for this section is number one, we need to know how to graph the exponential function and understand the exponential function with the base e. So e is another number like a pi. And three, performing the calculation involving exponential expression. And number four, we use application for the exponential function, which is this is a very popular the application that we might see in our real life. Graph of the exponential function. As the name implies, the exponential function involves the exponents. However, unlike quadratic functions, which have a variable with the exponents of 2, or polynomial functions, which often have a variables with the exponent of 3, 4, or higher, or even rational functions, which has expression using the negative exponent. Exponential functions differ from all these functions we study in this course, and so far in that the variable is now the exponent. So we learn about the function was like x kind of square, x cubed as a polynomial, and rational was this one, right? But difference for the exponential function is we are learning as 2 to the x, 3 to the x, like this. But base cannot be negative, but it could be the half. Half of 2 to the x power is fine. Because the definition of the function is the form of the b to the x. Okay, this is a basic function. But there's a restriction for the base b, which has to be positive or not equal to 1. It's called the exponential function with the base b. There are two requirements on the base of exponential functions. Number one, we must have a b not equal to 1 because f of x equal to 1 to the x makes a constant function. So we don't want 1 on the base. Number two, we must have a b is a positive or the greater than 0 or positive. Avoid the non-real complex functions. Which means if you have a negative, like a half of this is actually the same as this, which is not a real number. So this is not a real. Okay, so we don't want to talk about the not real case, which is you can't really find the points on the plane. Let's start our discussion on the graphs of the exponential function with the simplest exponential function of f of x equal to 2 to the x power. So yeah, I use a base 2. Without knowing much about the function f of x equal to 2 to the x yet, we will evaluate the function for the several x values, which means when you use a 0 power, is always any 0 power to the base is a 1. And then negative 1, which is negative 1, you can always change to positive as a 1 over 2. When you have a negative 2 power, same as 1 over 2 square, which is 1 over 4. Negative 3, so 2 to the negative third power, same as 1 over 2 third power, which is 1 over 8. 0 power is 1, but first power just stays a 2. Second power means that 2 times 2, 4. And then third power means 2 times 2 times 2 equal to 8. Let's go to the next page. The two charts display the trace of every exponential graph, a graph of that is essentially determined by the left and the right hand behavior. So first chart display the behavior of the f of x equal to the x on the left, while the second chart display the right side of behavior. So plot these points on notice on the following, which is I did, which means I use the table of, let me use color. So I use the table as, which is I already found it, negative 3 as 1 over 8, negative 2 as 1 over 4, negative 1 is 1 over 2, 0, 1, 1, 2, 2, 4, and 3, and 8. So you'll see those order pairs on here. And then if you connect them together with those points, yeah, this is what happens. This is the behavior of exponential function graph. So left side, when x goes to negative infinity, and then as you notice, it will approach to the 0, but not equal to the 0. Which means we have a horizontal asymptote, which means, so asymptote means graph try to getting closer to the asymptote, but never crossing and never touch. Right side unlikely, which is go to infinity to the x goes in the infinity. As you notice that the f of x also goes to infinity too. So there's no asymptotes. There are the traits that every exponential graph possesses. One end will flatten out toward the horizontal asymptote, while the other end will take away from the horizontal asymptote. So horizontal asymptote for this case is actually this is horizontal asymptotes, which means the graph not going to touch the x-axis at all. So we for these regions, drawing the graph of the even more complicated exponential functions can be accomplished with the simple two-step process. So number one, find the horizontal asymptote, which is we're going to practice that. And then we plot the 2 points, and then we'll see the behavior of the graph. All right, let's consider the following 4 exponential functions. So f function, g function, p function, r function. So because this is the exponential, because as you notice, all the x is in the exponent place. Right? Okay. And then we will visit the chapter 1 discussion regarding the graph of the g of x equal to a times x minus h squared plus k as a transformation of f of x equal to x squared to help to give insight into how we determine the location of the horizontal asymptote for the exponential graph. So for f of x equal to a times x minus h squared plus k, so h represent the shift graph of the left or right. A represent the stretching, compressing the graph, possibly reflection across the x-axis. The case is actually the when a is less than 0, okay? And then we also have k, which is right here, which is to give us the shifting of the graph up and down. So starting with f of x equal to b to the x power that has the horizontal asymptote equal to y equal to 0, which is same as the x-axis, and the consider g of x equal to a times b to the x to minus h power plus k. So same thing, h represent the shifting to the horizontal asymptote, which is right here. This is a horizontal asymptote shifting. Right, it's going to be up and down. And then the a stretching, compressing, reflection of the x-axis across x-axis. And then the against yeah, oh yeah, h is left and right, and then the where is actually the k here with the x-axis leaving the okay. And then as you notice, the k is going to be the shifting up and down. So when you look at this, we have to look at what is represented here. So yeah, so horizontal asymptote is coming from the k. So when I look at the first problem, so this time a is a 1, b is a 5, and then h is a 0, minus 0, and then plus k is a 0 too. So for the horizontal asymptote from here, so you can say y equal to 0. For the g function, a is a -3, b is a 2, h is a 1, and this is a k. So y equal to 4 is a horizontal asymptote. C, a is a 1, b is a 1/3, h is a -2, and then k is a -1. So y equal to -1 is a horizontal asymptote. A is a 1, b is a pi this time, h is a 4, but I don't see the k, which is a 0, so y equal to 0 is a horizontal asymptote. So now that we know the location of each horizontal asymptote, which is every exponential function has a horizontal asymptote, we can graph the curve by finding 2 points to determine which side goes toward the asymptote and which sides go away from the asymptotes. Because the domain of every exponential function is -infinity, and the x value can be used, but as we'll notice in the following graph, choosing x values that keep the exponent portion of each exponential function small is wise. So graph of each following the exponential function. So the k is a 0 for this one. So horizontal asymptote for this case is y equal to 0, which means we can put that in here. And then I can use a table, which means I think I want to use a -1, 0, and 1. So 5 to the -1 is 1/5. 5 to the 0 is 1. And then 5 to the first power is a 5. So if I plot it in, so -1, 1/5, very close to 0, and a 1, and then 1, 2, 3, 4, 5 right here. So this is a graph of 5 to the x power. Okay? All right. In the B, okay, so the y equal to k is a horizontal asymptote, right? Which is y equal to 4 this time. So y equal to 4 means 1, 2, 3, 4 right here. So this is a horizontal asymptotes. And then if I use a table, but this time I'm looking up the x minus x, okay? And then I just set x minus 1 equal to 0. And so for x equal to 1. I'm going to put the 1 in the middle. And then 2, and then 0. So put the number in the as a sequence, okay? And then if you plug it in with a 0, so negative 3 times 2 to the 0 minus 1 plus 4. And then you get negative 3 times 2 to the negative 1 plus 4. And then you got negative 3 times 1/2 plus 4. And then you get negative 3 over 2 plus 4, which is 8 over 2, which is same as a 5 over 2. So 2.5. So when x is 0, it's going to be 2.5. So 1 and 2.5 right here. Which just makes a y intercept, right? And then you plug it in 1, so negative 3. Sorry about that. And then we plug it in 1, so 2 to the 1 minus 1 plus 4, which is a negative 2. 3 times 2 to 1 minus 1 is 0 power 1, right? So it's going to be a 1. Okay, so 1 is 1 right here. And then 2, plug it in 2, right? So negative 3 to 2 minus 1 plus 4. You got negative 3 times 2, so 2 plus 4. So negative 6 plus 4, which is a negative 2. So 2 is negative 2 right here. So this time is graph is upside down because of negative reflection in here. So you'll get the graph looks like it's going down this way, okay? Yeah, so upside down graph. But still, graph's not going to be above the 4. And C, P of x equal to 1/3 to the x plus 2 this time. So horizontal asymptote for this case is y equal to negative 1. So put the horizontal asymptote. And then this time we'll see the graph above because A is a 1 positive, okay? So table. So I use this time, which is I use x plus 2, set it up equal to 0, x equal to negative 2. So I'm using negative 2 in the middle. And then negative 1, and then the negative 3, what am I, sorry? And then negative 1. So plug it in. So 1/3 to the negative 3 plus 2 minus 1 is, it's a negative 1/3 to negative 1 minus 1, which is negative 1/3 to negative 1 is same as 3. Okay, and then the minus 1, so which is 2. So negative 3, actually the 2. So 1, 2, right here. And then negative 2, so 1/3 to the 2 plus, negative 2 plus 2, which is a 0. So which is 1 is equal to 0. So 1 minus 1 equal to 0. So when negative 2 is going to be the 0. And the negative 1 is 1/3. Negative 1 plus 2 minus 1. So 1/3 to the first power minus 1 is 3. 1 minus 3, right? So negative 2/3. So negative is negative 2/3. Right here. So your graph is going to be this. It's still above the horizontal asymptote. Now the D, which is horizontal asymptote is a 0, which is this one. And then your graph will be above it. And then table. And then you get the, this time is x minus 4 equal to 0. So x equal to 4. I put the 4 in the middle. And 5 and 3. Plug it in. Pi 3 minus 4, which is pi to the negative 1 is 1 over pi. So 1 divided by pi is, actually I should have get this. So 1 divided by pi, which is pi is 3.14. So if you use a calculator, then I'll get it as 1 divided by pi. Then I got 0.318 something, okay? So 0.3. So 3, 1, 2, 3 is a 0.3. So close to 0. And then 4, so pi 3, 4 minus 4, which is a 0, which makes a 1. So 4 is 1. And then 5 minus 4, which is a pi, which is a 3.14. So 5, 1, 2, 3, 4, 5, 1, 2, 3.4. Yeah, so your graph will be this too. And then still stays above the x-axis, okay? Alright, let's look it up the next page. The natural exponential function, which is, we are using the base e this time. So in order to get an e is the value of this is going to be a e, which is coming from this function though, which is we are using as a base, okay? So for the purpose of this course, the calculator will be used to determine the expression involving e. So if you use a e, which is k is a 0 still, so we have a horizontal asymptote equal to y equal to 0, and then use a table, and then you can use the x equal to 0, which is negative 1, 0, 1 looks good. So e to the negative 1 is same as 1 over e. So 1 divided by e, but you can find e from the ln, okay? If you look at the ln from your calculator, and then, yeah, you can just use a calculator, okay? So 1 to the divided by, or you can just put the negative 1 power to the first power this time, right? So I got about 0.4. So negative 1 is 0.4, still above. And then 0, of course, is 1. And the e to the first power, but e is about the 2.1, 2.7 and 1.828 like that, right? So it's about 3, right? So still less than 1, 2, 3 right there. Okay, and then you can connect this. So this is the graph of. So e is about less than 3, but still greater than 2. That's the value of the e. Okay, the next one. Okay, so we got those. Okay, next one, I have g functions, which is a negative 2 times. So horizontal asymptote for this one is y equal to 5. So you got 1, 2, 3, 4, 5 right there. So we have a horizontal asymptotes to here. Okay, table. Oh, I think let me use it here. So this time, this is x plus 3. So if you set the x plus 3 equal to 0, x is a negative 3. So I put the negative 3 in the middle. And then negative 2 and negative 4. So I got negative 2 times of e to the negative 4 plus 3 plus 5. And then you can use calculator, okay? So we got to use calculator. So negative 2 times. And then e to the power of negative 4 plus 3. And then make sure plus 5. Then you said 4.3. So negative 4, 1, 2, 3, 4 is going to be the 4.3. So 1, 2, 3, 4.3 right there. Negative 3. So negative 2 times e to the negative 3 plus 3 plus 5. So this is a 3. So negative 4 is 3. 1, 2, 3. And then negative 2, e to the negative 2 plus 3 plus 5. I have to use a calculator. So negative 2 times e to the first power. Negative 2 times e to the first power. And plus 5. I got negative 0.4. 3 something. So negative 2 is going to be negative 0 right here. I don't know what that is. Okay, it's not there. So if you grab this, it's going to be something like this. And on this side, of course, it's going to be getting close to this one. So calculation involving the exponential expressions when working with e in example 3, we use approximation e as 2.718. But you have a calculator to use, so don't worry about the memorizing it. For our continued use of E and for evaluating most exponential expressions, we will be using calculator. Yeah, that's what I told you, right? When studying exponential expression, using a calculator, two button becomes useful. So for most calculator, as important button will be typically one of the following. So you might see this form, or this, or hat, or X. So each of this can be used to find any number raised to any other number. And also YouTube's, if you find it as YouTube, it shows a very shows good details about how to compute. To verify a button on your calculator is the exponential button is in question to practice how to use a button and calculate the following the round to decimal place. So 3 to the x power. So this time you might push the button 3. Okay. And then you might want to use a head button. Okay, and then put the 2.8, and then you will see those numbers. Same as 2.4 to the 1.9 power. So this first button works well for the finding the value of the exponential expression for any numbers you wish to type into a calculator. Earlier we discussed the number E, which can be approximated as 2.7186. I think this is 6182, blah, blah, blah. This is not a number that I would ever wish to type in or even memorize. So I just use a calculator. This is where the second calculator button become useful, because you need to use a second to find the E number. Most calculators have one of the following buttons, so you'll see those: E to the head, E to the x power, or E. Because the calculator often vary with how to use this button, some require the power to be typed prior to hitting the button too. So yeah, if you have, I think the Casio only shows the answer, and that's what you need to do. So if you have I told you that if you're having trouble to answer it, okay, you just need to watch the YouTubes. So just say, okay, how do I use this calculator to find this like that, okay? So verify the button on your calculator is the exponential button in question, and practice how to use this button by calculating the following, rounded to the decimal places. So e to the 2 to the 7th power and e to the negative the 0.4 power. And then you'll get those value on the right. Exponential application. Whether the calculated or added to the saving account or charged because of the carried balance on a credit card, interest is the most common example of the application involving the exponential function. So consider 4,000, which is a principal, 6%, which is a rate, the annual interest rate, for 3 years, which is T, but the interest calculated to pay monthly for the 30-60 month, which is every month. Actually, we try to figure it out without the formulas, okay? So first month, if you multiply it, 20 is interest. So from the principal, and then the next month, you'll see, or at the end of the month, you'll see the 4,020. For the second month, you use the 4,020 with the 0.06 for the another month, and then you get this much of the interest, which is a little bit more than the first month. And then add it to your principal, and then you get those. And then do it again for 36. It's going to be a lot of work. Considering the first three calculations, we'll see the monthly interest started at the 20 is slightly increasing every month. Over the entire 36 months, the total interest when paid monthly will be greater than the simple interest calculation of the 720. So simple interest means you just need to put for the balance of principal times rate times the time, which is interest, and then adding to the principal. But I think they're just talking about principal. So in order to just get a principal, the interest, you just need to use the interest is a PRT. Okay, so which is the P is this time is 4,000, 6% for 36 months is 3 years. So you have to use those. So 3 times, okay? So if you multiply them together, and then you got 4,000 times 0.06 times and 3, yeah, you got 720. But how do we find the total interest over 36 months when the interest is paid monthly? So this is for 3 years. Now, what about monthly? Useful described as we call the compounded monthly, which is we call the compounded interest without doing the 36 separate calculation like this. That's too much. All right, so next example. This is where we can use the exponential function. So in general, the formula for calculating the account balance of P dollars at an annual interest rate of R compounded n times a year for T years is, this is the formulas. So, example 1, calculate the ending balance of the 4,000. So P is a 4,000. For the 6%, which is R is 0.06. And then N is actually the telling you from here, monthly, which is a 12 month. And then T for 3 years. And then plug it in. So A is P 4,000 of 1 plus 6% over 12 months, 12 times for 3 years. And then this time you gotta use calculator. So 4,000, 1 plus 0.06 divided by 12, and then power of the 12 times 3. Make sure that you need to put the parentheses around 12 times 3. Or otherwise, you can just put 36. I got $4,786.72. So interest is what? $786.72. Example 2. We have a balance of the 5,700. And the interest rate is 45%, which is 0.045. And then it's a daily, which is there are 365 a year. And then for time is 6 years. So amount will be 5,700. 1 plus 4.5% over the 365 days. 365 for 6 years. So use a calculator. 5,700, 1 plus 0.045 divided by 365 and power of parentheses 365 times 6. And then I got $7,466.67. So make sure you rounded it to the hundredths place too, right? Because we use the money as cents in hundredth. Anytime there is interest is calculated, the higher frequency of the time interest is compounded will always result in more interest, even if the difference is minimal. And that being said, there is a limit to how much interest can be earned regardless of the interest compounding frequency. So this leads to second formula for the calculating account balance, with give the maximum amount balance regardless of the frequency of the compounding interest. So the next one we call the continuously compounding interest. So compounded continuously. So we actually converted it to the, I told you here 1 plus 1 over n to the n is going to be an e, right? So that's what we switch it from the compounded periodically to the compounded continuously. So example 3, calculate the ending balance of 4,000. But e to the r is a 6% to the 3 years. So use a calculator. So 4,000, find the e from the ln, and then 0.06 times 3. Then I got $4,788 and then you got the 87 cents. Don't say every 86, okay? Because there's a 9 after 6. For the example 4, calculating the end balance for the 5,700 at the 4.5% compound continuously for 6 years. So same problem from the previously. So 5,700 e to the 0.045 times by 6. So 5,700 e to the power 0.045 times 6. And then 7,466, now you can say 80 cents. All right, so when you compare this amount from the previous amount, you do notice that this is a little bit bigger than the compounded periodically. Alrighty, so this is about the exponential functions, okay? Alright, thank you for listening.